I see that you have your computers that you download this file now, and we start taking a look at what we have in here. So, let's come back. Again, we're going to deal with problem number 1. Problem number 1, it's a very similar test to the one that we did here, but downstairs in the fancy triaxial cell that I have in my laboratory with very precise and accurate measurements of strain and stress. All right, so while you download that file, let me show you something else. Okay, if you take a look at the file that you're going to download, it's called Mancos Unconfined 100 PL7. PL7 stands for Parallel Sample Number 7. And here I have some videos of it, of what this sample looks like when it is fed. This is a shade sample, and you can see more or less clearly, I hope that you can appreciate from where you are, that this is the bedding. It's a sample parallel to bedding, and this is what it looks after it was broken with X-ray tomography. So you see, similar to the sample that we broke in the previous case, you see a shear plane, and then you, in this case, you see some other planes aligned with the bedding. All right, let me pause this, and now let's go to the file. You have the file?
Yes.
Yes? Okay. So, same thing as before, just copy the file and paste it into a new file. For the people using Mac, you remember about talking the Control F, and then you couldn't find the advanced, the replace. What you have to do is you just Control F, and then in the corner, there is another window, there is another thing to open a new window, and then you put advanced search, and in advanced search you can do replace, search and replace. All right, so it looks like we need to separate this data. So we're gonna go text to columns. You know how to do this. We're gonna use space.
He meant by search.
Be careful sometimes that
Control F.
when you do the separation of the data, probably your header is going to be separated too, and then you have to fix it. So I'm going to fix it now because it was separated, but that separation was not meaningful for the header.
I think if you just copy and paste from the data without importing it, it just automatically separates them.
Oh, okay, okay. I'll try that next time. But now I'm already halfway through this. Thank you.
Mm-hmm. Yep.
All right. So I fixed the header, and we have time, force, displacement in axial direction, which is this one, and this one is displacement in radial direction. So let's do the first thing that we did for the other sample. We're going to compute stress. Okay? Let's see, the diameter for this one, I think, was like almost exactly 1 inch. Yeah, it is 1 inch. So the area of the sample is going to be, as we said, it was 0.785, right? Daniel, is that
Yep.
correct?
Yep.
Inches squared. Therefore, the axial stress in PSI is going to be equal to here the force, and this force in this case, it doesn't start at 0, but that's fine, okay? Don't worry about that. That's the actual reading of force. So force divided by area. You know these guys tricks, these trick guys? When you're in a cell and you press F4, it automatically adds those currency signs so it gets locked. And now I can copy this, and I get stress as a function of time.
I forgot what it was. Oh, FM. Is it?
All right.
FM.
So let's plot now. Well, no, let's hold on the plotting. Let's before see if we can get the strains. We said before that the diameter was 1 inch, and the length, if I remember correctly, it's 2.01 inches. Let me check that. Yes, that's about it. Okay, so first, let's do the axial strain. Axial strain doesn't have any units, and it's going to be equal to the change of length, this one minus that. That's going to be change of length, divided original length, I lock it 2, and that's going to be the axial strain. And let's see what we get. Okay, I think it should be fine. Notice that at the beginning you might get some negative values, but those negative values are very small, so don't worry about it. Let me compute now the radial strain. Again, it's change in length divided the original length. In this case, the original length is that. Oh, I forgot to log that one. So that should be the bottom. So now we have axial stress, axial strain, and radial strain. Okay? Are you guys there? All right. Let's plot what's going on in here. Let's first plot axial stress versus time. So I'm going to use this type of scatter plot. This force is not stress. I'm going to change it now. Okay, now it's in terms of stress. And it's similar to the other file that, and the other data that we did in here. And what is going to be the peak stress for this particular test? Probably you can move the mouse over your data and tell me the exact value. In the meantime, I'm going to add some legends, some titles. And here, this is axial stress, PSI, and this one is time. The peak stress in this particular case is the maximum value that the sample took, this shale sample, and it is value somewhere around there. I don't know why it doesn't show up. it is 37 something. Okay? That's in stress. Okay. Let's first check the strains before plotting them. So I'm going to make another plot over here where I plot as a function of time strains. So this is the axial strain, and I don't know if you know this trick, guys, but you select a plot, you do Control C, Control V, and that's going to add another plot that you just selected, and then move it. I have the other plot right there. So now we have the axial strain and the radial strain. So this is axial, this is radial. And let me limit this to 3000. So, okay, now I have stress. All right. Okay, are you there? We have stresses, we have strains. I'll give you 1 minute to catch up, okay? If you have any questions, just let me know. Yeah. Yes, axial strain, radial strain. Which one? Okay. Yes.
Hold down control. I mean, there are other ways.
Yeah, so that's equal to the change. So now this axial stress is force divided by V. The area was 0.785, but it's basically the diameter squared times pi divided by 4, right? So just for the sake here of completing my plots and my equations, this one is equal. It's not that I don't believe Daniel with his number, but I'm just going to do it again, okay? So 5 times diameter squared divided by 4. And that's the area. Okay. All right, guys, are you there? So we have stresses, we have strains. The next step is to plot stress as a function of strain. What we're going to do is we're going to pick this one, and instead of plotting in the x-axis time, I'm going to move this one and plot axial strain. And the result, so we can see what's going on here. Move this one over here, this one over here, This is what you should get. Okay, so the only thing I did was I copied this plot and then just redid it, but now I'm plotting in the y-axis stress, in the x-axis this is strain. And strain doesn't have any units. And this is what we wanted to get. Now we have stress as a function of strain. And as you can see, the higher the strain, the larger the stress. And the proportionality between stress and strain gives me the Young modulus. For this particular problem, I am asking you to compute the Young modulus in this interval. If you see the statement of the problem says, compute Young modulus and Poisson ratio between 0.25% and 0.4%. And that's here, in this region. Why? Because usually at the beginning of loading, it's not accurate to measure the Young modulus because sometimes you're closing some small cracks or you're just taking care of the end faces of the rock that may not be perfectly parallel, and that's why this is not equal to this part. And when you continue further on, the rock starts to break, and that's why you don't have to mention it there either. Usually in standards, for example in the future, if you get analysis of the rock mechanics laboratory, they will give you this type of data and they will report the Young modulus usually at 50% of the loading, which in this case will fall somewhere over here, okay? But it's not going to be too different to what you're going to compute. I like that you notice in this data that we have this main train, which is the loading part, but also we have these other things. Can anyone tell me what are these small things over there?